In 1851, at the Great Exhibition in London's Crystal Palace, a machine was unveiled that could cut gears with precision measured in 10,000ths of an inch. No electricity, no computers, no digital controls, just mechanical ingenuity, crafted by hand, operating with accuracy that modern machinists struggle to replicate. The engineer who built it used techniques we've forgotten, methods we can't reproduce. And when that generation died, the knowledge died with them. We think of the 1800s as primitive. Steam engines, horse-drawn carriages, gas lamps, a world waiting for the modern age to arrive and fix everything. But what if we're wrong? What if the 19th century wasn't behind us, but ahead of us in ways we don't understand anymore? Because scattered across museums, forgotten in patent offices, and buried in engineering journals, are machines from the 1800s that shouldn't exist. Devices so precisely made, so elegantly designed, so far beyond their time, that modern engineers look at them and ask one question: how?
How did they achieve tolerances we need computer-guided mills to produce using only hand tools? How did they build mechanisms so complex that we need CAD software to understand them, with nothing but pencil and paper? How did they create materials so durable that their machines still work 200 years later while ours break after 10? This isn't about romanticizing the past. This is about lost knowledge, techniques that were never written down, skills that took a lifetime to master and died with the craftsmen who held them. Welcome to the Financial Historian, where we follow the tools, because the tools built civilization. Today, we're asking the uncomfortable question: did the Industrial Revolution give us progress, or did it trade mastery for speed, quality for quantity, and knowledge for profit? Because the machines of the 1800s weren't just different. In some ways, they were better. And we can't build them anymore.
Let's start with something impossible. In 1900, divers off the Greek island of Antikythera discovered a shipwreck. Inside was a corroded lump of bronze. When researchers cleaned it, they found gears. Over 30 interlocking gears, arranged in a mechanism of such sophistication that it took a century to understand what it did. It was an astronomical calculator, built around 100 BC. It predicted eclipses, tracked planetary positions, and calculated the timing of the Olympic Games. The engineering was so advanced that nothing comparable appeared again until the 14th century. 1,400 years later. We call it the Antikythera mechanism, and it's proof that civilizations can reach incredible technological heights and then lose that knowledge completely. The 1800s had their own Antikythera moments. Machines that were built, worked perfectly, and then the knowledge of how to build them vanished. Take the Jacquard loom. Invented in 1804 by Joseph-Marie Jacquard, a French weaver, it's the machine that automated textile production. But calling it a loom undersells what it actually was. The Jacquard loom was a programmable computer, made of wood and metal. It used punch cards, holes punched in stiff paper, to control thousands of threads simultaneously, weaving patterns so complex that even today's digital looms struggle to match them.
Each card was a line of code. Each hole was an instruction. The machine read the cards, lifted the correct threads, and wove patterns with mathematical precision. You could change the pattern by changing the cards, reprogram the machine by rearranging the deck. Charles Babbage saw a Jacquard loom in 1836 and realized something profound. If punch cards could control a loom, they could control a calculating machine. That insight led to his analytical engine, the conceptual ancestor of the modern computer. But here's the part we forget. The Jacquard loom wasn't just conceptually advanced, it was mechanically perfect. The tolerances were so tight that cards fed smoothly at high speed without jamming. The gears meshed without backlash. The threads never tangled. And it did this for 12-hour shifts day after day for decades. Modern textile engineers have tried to replicate 19th century Jacquard looms. They can't. The precision required to make thousands of moving parts work in perfect synchronization without computer-aided design or CNC machining is beyond current practice. We know what the machine did. We have surviving examples, but we can't build a new one that works as well. That's not because we lack the tools. It's because we lack the knowledge. The craftsmen who built Jacquard looms didn't follow blueprints. They felt the tolerances, adjusted by sound, filed metal by hand until it fit perfectly. That skill took 20 years to develop. And when factories replaced craftsmen with assembly lines, that skill disappeared. The same thing happened with marine chronometers. These were the GPS of the 1800s. Clocks so accurate they could keep time at sea, allowing sailors to calculate longitude and navigate across oceans.
John Harrison spent 40 years perfecting his chronometer. His H4 model, completed in 1759, lost only 5 seconds over 81 days at sea. In the 1800s, chronometer makers refined Harrison's designs even further. Swiss and British workshops produced clocks accurate to within 2 seconds per day in conditions of temperature variation, humidity, and constant motion. Today, we have atomic clocks accurate to a billionth of a second, but we can't build a mechanical chronometer as reliable as the ones made in 1850. The knowledge of how to handcraft escapements, balance springs, and jeweled bearings to that level of precision is gone. We have the surviving clocks. We can measure them, study them, but reverse engineering isn't the same as mastery. Because mastery isn't about understanding what a machine does. It's about understanding why every microscopic detail matters. And that knowledge wasn't written down. It was passed from master to apprentice in workshops over decades. When the workshops closed, the knowledge ended.
Here's where it gets strange. The machines of the 1800s were built with tolerances that shouldn't have been possible. Because to build a precision machine, you need precision tools. And to build precision tools, you need even more precise machines. It's a loop, a bootstrap problem. So how did the Industrial Revolution start? The answer is by hand. Literally. Henry Maudslay, the father of precision engineering, built the first truly accurate lathe in 1800. Before Maudslay, lathes were crude. They wobbled. The cutting tools drifted. The parts they produced were inconsistent. Maudslay's lathe was different. It had a lead screw, a sliding tool rest, and a rigid frame. It could cut threads with consistent pitch, turn cylinders to uniform diameter, produce parts that were interchangeable. But here's the paradox. To build that lathe, Maudslay had to hand-file every critical surface flat. He checked flatness by coating metal plates with soot and rubbing them together. High spots left marks. He filed those down. Repeated the process thousands of times until the surfaces were flat to within 1/1000th of an inch. That's the precision required to build a precision machine. And he did it by hand. No machines to help him, just files, scrapers, and an obsessive attention to detail. Once Maudslay had his lathe, he could build more lathes, and those lathes could build milling machines, and milling machines could build planers, and planers could build gear cutters. Each generation of machines more precise than the last.
By the 1850s, workshops like Maudslay's and Joseph Whitworth's were producing machines accurate to 100,000th of an inch. Whitworth's measuring instruments could detect variations invisible to the naked eye. His standard screw threads became the basis for modern engineering. But the method was still the same: hand scraping, hand filing, hand checking with blackened plates, and intuition. Modern CNC machines can produce parts to millionths of an inch, but they're programmed. Set them up wrong, and they'll produce a million identical, defective parts. A 19th century machinist couldn't hide behind automation. Every cut was manual, every measurement was tactile. If the part was wrong, you felt it immediately. That forced a level of skill we don't teach anymore, because we don't need to. Our machines do the thinking. But when the power goes out, or the software glitches, or the CAD file corrupts, we're helpless. The machinist of 1850 wasn't. And that's the paradox. We have better tools, but worse skills. We can produce more, but understand less. There's a term for this in manufacturing: de-skilling. As machines get smarter, workers get dumber. Not because people are less intelligent, but because the knowledge moves from the human to the machine. And when the machine breaks, or the technique is needed but unavailable, the knowledge is gone. The 1800s didn't have that problem, because the knowledge was in the people, not the tools.
The machines are only half the story. The materials are the other half. And some of the materials used in the 1800s are better than what we make today. Take Damascus steel. For over 1,000 years, swordsmiths in the Middle East forged blades with a distinctive wavy pattern. The steel was incredibly strong, held a sharp edge, and was flexible enough not to shatter. European crusaders called it the finest steel they'd ever seen. The technique was lost around 1750. No one knows exactly why. Maybe the ore source ran out. Maybe the master smiths died without passing on the secret. But by the 1800s, Damascus steel was already a legend. Modern metallurgists have tried to recreate it. They've analyzed surviving blades, studied the carbon content, the grain structure, the impurities. They can make steel that looks similar, but it doesn't perform the same. Because the difference isn't just chemistry, it's process. Damascus steel was folded and forged hundreds of times. The temperature had to be exact. The rhythm of hammering mattered. The smith knew by sound, by color, by feel when the steel was ready. That's not something you can write in a formula. It's embodied knowledge. Knowledge that died with the craftsmen. The same thing happened with concrete. Roman concrete, used to build the Pantheon and the Colosseum, is still standing after 2,000 years. It's stronger now than when it was poured. Modern concrete starts cracking after 50 years. The difference? Romans used volcanic ash, specifically a type called pozzolana from the region around Mount Vesuvius. Mixed with lime and seawater, it created a chemical reaction that made the concrete self-healing. Cracks would fill with minerals over time, making the structure stronger.
We know the ingredients, we have the formula, but we can't replicate it at scale. Because the volcanic ash from Vesuvius has a specific mineral composition. Ash from other volcanoes doesn't work the same way, and the Romans didn't document which quarries they used, or how they processed the ash, or what ratios worked best for different applications. That knowledge disappeared when the Roman Empire fell, and we're still trying to figure it out 1,500 years later. The 1800s have their own material mysteries. Victorian-era cast iron is absurdly durable. Bridges built in the 1850s are still carrying traffic. Railings, lampposts, and machinery from that era still function perfectly. Modern cast iron doesn't last as long. It's more brittle, more prone to corrosion. The difference is in the smelting process. 19th century iron was smelted in small batches using charcoal and stone furnaces. The slow, low-temperature process removed impurities and created a fine grain structure. Modern iron is smelted in blast furnaces using coke at much higher temperatures. It's faster, cheaper, but the metallurgical properties are different. We can't go back to charcoal smelting. It's too slow, too expensive, doesn't scale. But that means we can't make iron as good as the Victorians did. The same applies to glass. Cathedral stained glass from the 1800s has colors we can't reproduce, the reds in particular. They used gold chloride as a colorant,
The process was dangerous, required precise temperature control, and produced inconsistent results. But when it worked, the glass glowed with a depth and richness modern glass can't match. We know the chemistry, but chemistry isn't enough. The medieval and Victorian glassmakers worked by intuition. They adjusted the furnace by sight, judged the viscosity by how the glass flowed off the blowpipe, added colorants based on experience, not measurement. That's artisan knowledge, and when the artisans retired or died, the knowledge went with them. So, yes, we have better materials in many ways. Stronger alloys, lighter composites, materials designed at the molecular level. But we've also lost materials. Not because we can't analyze them, but because we can't recreate the conditions and expertise that made them possible.
So why did we lose these techniques? If the machines were so good, the materials so superior, the knowledge so valuable, why did it disappear? The answer is simple: economics. In the early 1800s, manufacturing was slow. A master craftsman might spend 6 months building a single marine chronometer. A Jacquard loom took a team of specialists a year to complete. Damascus steel swords were made one at a time, each unique. That's not scalable. And by the mid-1800s, the industrial economy demanded scale. Factories needed to produce thousands of identical parts, fast, cheap, consistent. That required standardization, interchangeable parts, assembly lines, mass production. And mass production killed craftsmanship, because you can't mass produce mastery. You can't train 10,000 workers to have the hand-eye coordination and tactile sensitivity of a master machinist. You can't replicate 20 years of apprenticeship in a 2-week training course. So factories didn't try. They simplified the work, broke complex tasks into repetitive steps, hired unskilled labor, paid lower wages, and made up for the loss in quality with volume. The factory owner didn't care if the product lasted 200 years. He cared if it sold this year, and if it broke in 10 years, the customer would buy another one. That's not a flaw. That's the business model. Planned obsolescence didn't start in the 1950s with light bulbs. It started in the 1850s with steam engines, textile mills, and railroads. The moment production shifted from artisans to factories, durability became a liability. Because a product that lasts forever is a product you only sell once.
So the factories built machines that worked well enough. Not perfectly, not forever. Just long enough to justify the price and break soon enough to justify a replacement. And the craftsmen who could build better machines, they couldn't compete. Their products cost more, took longer, required expertise that customers didn't appreciate. By 1900, most of the great workshops were gone. Maudsley's shop in London, Whitworth's in Manchester, the Swiss chronometer makers, the French instrument builders, all outcompeted by mass production. The knowledge didn't disappear overnight, but it faded. The masters retired. The apprentices found factory jobs. The techniques weren't written down because they couldn't be. You can't teach hand scraping in a textbook. You can't describe the feel of metal under a file or the sound of a properly meshed gear. And by the time anyone realized what was being lost, it was too late. There's a term in manufacturing, technological inheritance. Each generation builds on the tools and knowledge of the previous generation. But if a generation is skipped, if a technique isn't used for 50 years, it becomes nearly impossible to recover. Because the tools are gone, the experts are dead, the economic incentive is gone, and no one remembers why the old way was better. That's where we are now. We have 19th century machines in museums that we can study but not replicate. We have materials we can analyze but not produce. We have drawings and patents and descriptions, but not the embodied knowledge that made them work. And unless someone deliberately tries to recover those techniques, they're lost forever.
Let's be clear. Modern technology is extraordinary. We have computers, smartphones, MRI machines, space telescopes. We've split the atom, decoded the genome, and landed robots on Mars. The 1800s didn't have any of that. But they had something we don't. Durability, repairability, craftsmanship that lasted lifetimes. A pocket watch from 1850, if maintained, still works. A smartphone from 2015 is obsolete. Not because it broke, because the software stopped being supported. A Victorian-era bridge is still carrying traffic 170 years later. A modern concrete overpass needs repairs after 30 years. A Jacquard loom from 1820 could be repaired by a skilled mechanic with hand tools. A modern CNC textile machine requires proprietary software, specialized parts, and a technician flown in from the manufacturer. We've traded longevity for convenience, mastery for speed, quality for quantity. And that trade made sense. It gave us cheap goods, mass production, a higher standard of living for billions of people. But it came at a cost. We lost the knowledge of how to build things that last, how to work metal by hand, how to judge quality by touch and sound, how to design machines that could be understood and repaired by the people using them. That loss doesn't matter until it does.
When a supply chain breaks, when a factory closes, when a critical part is no longer manufactured, when the only people who know how to fix something are retired or dead, then we're stuck, because we've outsourced the knowledge to specialists, corporations, and machines. And when they're unavailable, we're helpless. The craftsmen of the 1800s weren't helpless. They could make or fix almost anything, because they understood materials, mechanics, and mathematics at a fundamental level. We've gained efficiency, but we've lost resilience. And in a world where supply chains are fragile, where geopolitical stability is uncertain, where access to advanced manufacturing could be disrupted, resilience matters. Were the machines of the 1800s more advanced than ours? No, not in capability, not in output, not in speed, but in some ways in precision, in durability, in the knowledge required to build them? Yes, absolutely. Because advancement isn't just about what a machine can do. It's about whether we understand how it works, whether we can repair it, whether we can build it again if we need to. And by that measure, we've regressed. The Industrial Revolution gave us incredible power. It transformed the world. But it also created a dependency on factories, on supply chains, on expertise concentrated in a few hands. The artisans of the 1800s didn't have that dependency. They were self-sufficient, not because they rejected progress, but because they embodied it.
When we look at a Jacquard loom or a Harrison chronometer or a hand-scraped Maudslay lathe, we're not looking at primitive technology. We're looking at the peak of human craftsmanship, the result of lifetimes spent perfecting techniques that we've chosen to forget. And maybe that's fine. Maybe mass production was the right choice. Maybe the trade was worth it. But we should at least acknowledge what we lost. Because those machines weren't just tools, they were knowledge made physical, mastery turned into metal, a record of what humans could achieve when skill, patience, and understanding were valued above speed and profit. And if we ever need that knowledge again, if the factories stop, if the supply chains collapse, if we have to rebuild from scratch, we're gonna wish we'd written it down. The machines of the 1800s weren't more advanced, but the people who built them were. And we can't build those people anymore. If this made you see the past differently, subscribe. History isn't about what we gained, it's about what we traded away. And I'll show you the cost every time.